Welcome. I'm Fran.
I'm Chris.
I'm causing feedback. I might have the clicker the right way round. Dramatic pause. Here's a slide you've seen earlier. So if you want to download the overview of the workshop, that's the first link.
Mm-hmm.
If you want to do some Java development, you might need Java installed.
That would be helpful.
Which is the second link, but you can probably manage to find that yourself. Or like I said, just pair up with someone if you want to try out the code, or look over someone's shoulder. So there's going to be some talking and some doing, or looking over someone's shoulder, depending on what mood you're in. Happy for me to move on? Yeah. Welcome. Right. So we've just introduced, there's a link to the slides and there's some code you can just download from there, or you might want to try it yourself from scratch. We're going to work through this, how do you say it? JCLEC, all right, library. We're going to look at the OneMax problem, see if a computer can make things big. Make things be 1 instead of 0. Then we're going to have a little go at coding your way out of a paper bag. And then we're come to the main reason for being here this afternoon, which is to see if we can actually make ourselves unemployed by our computer generating the code for FizzBuzz for us. If you saw my lightning talk, I gave you a speed overview of it, but we go through a few more details now.
Yeah, if I could just add to that one, what we would like you to take away is a kind of understanding about how these things work, so that you can understand the ideas behind how code can generate code, but also an opportunity for you to get your hands on and play with it as well. Because we can talk about it and we can go through slides, but it's not the same as you getting your hands on and tapping that keyboard and having a go. Okay, thanks, Fran.
So we're going to talk about evolutionary computing and get a clearer idea of what that means. And then, as we said, we'll move on to actually doing some of this. And then we'll use this JCLEC. Got it right. Library. For 3 different problems. I think you'll get the chance to do 2 of them, and the final one will sow some seeds, and there might be time for you to play with. We'll see how it goes.
Can I just mention one thing on that, Fran?
Mm-hmm.
Fran and I gave a very similar workshop last year, and we had great fun. And then we had this kind of conversation that says, hey, let's just apply this to FizzBuzz. What could possibly go wrong? Okay, and it turned out that we learned a hell of a lot by trying to get these approaches to work for FizzBuzz. So I hope we can get that over as well.
And there's still more to learn, and this has left more questions than it's answered.
Yes, exactly.
What did it do? God, crikey. So, you frequently apply machine learning type approaches and evolutionary computing approaches to optimizing something. Now that might be trying to make your code quicker. That's one use of the word optimize. Sometimes you want to make something have better quality, something be bigger. Sometimes you want something to be smaller, like the cost or the time things take to run. So basically we're trying to make things as big as possible, or big enough, or small as possible, or small enough. That's what we mean by optimizing. This means you have to start thinking about how you can measure things, and it's quite difficult to assign a measure to things sometimes, and that's going to come out in fitness functions and cost functions, which have caused a lot of head scratching for FizzBuzz, but I'm getting ahead of myself. So in some sense, we're after the best, or something at least that's good enough, or better than we managed to work out ourselves on with pen and paper. So we need to be able to define best. So we need to do some thinking. We can't leave all the work to the computers yet. So, okay, what's the problem? I just said you could sometimes work something out of pen and paper, but sometimes you can't. There are a variety of different types of problems. If you're trying to look for a number in a list or a vector, that's all right. Start at the beginning, walk your way through, and it's either there or not. To take ON at worst, because you might have to search all n numbers. If you've got your data sorted, maybe it's in a balanced binary tree, then it could be quicker. But not everything in life is lined up in a list for you neatly or ordered for you so as you can just search in smaller and smaller chunks to find what you're after. So if you're trying to do some kind of load balancing, that's not nicely laid out for you to walk along and work out what the best solution is there. That's hard. That might be quadratic at that point. And other problems are worse than quadratic. This just in essence means you can't work it out with pen and paper. You can't necessarily try every possible combination because there's just not enough time. But classic example is the travelling salesman problem. So if I wanted to go to each table in this room and put a paper bag on it, what's the optimum way of doing this? That might be I'm trying to minimise my steps because I'm in a hurry and we want to get to FizzBuzz nice and early. Or it might be I've got my phone in my pocket and it's counting my steps and I've only done about 3,000 today. So I might want to do as many steps as possible. So make it bigger, make it smaller. If I start listing the number of ways of walking to each table once and only once, I can do that with this many tables. If I did it with all the tables in the hotel, or actually all the tables in all the hotels in the whole world, which hotel do I start in? I can't work out the best thing to do there. I could randomly try a few approaches with pencil on paper, but then I want a way to hone in on something better. I'm getting ahead of myself again. That's a factorial problem. And then other problems get even more difficult. It's just explosive number of combinations. Typical examples, timetabling. Anyone ever tried to arrange a conference? Or has someone who's ever been a teacher who has set up a timetable? You've got rooms, you've got classes, you've got speakers or teachers. So you've got lots of things that can only be in one place at a time, but you've got to actually cover all the lessons and table plans for a wedding. So formal seating arrangements where you've got extra constraints of two relatives can't be anywhere near each other and two other people have to be near each other. It's incredibly difficult. Loads of people think, that'll be straightforward and try and do it themselves, and it's very hard. There's a guy who's a member of ACCU who's got a sideline business called something like Wedding Seat Planning, which is powered by genetic algorithms.
Is it really?
It is. He's got a nice little write-up of genetic algorithms there. We should have that on the slides as well. So, yeah, if you can work things out with maths, with a pencil, on a bit of paper, I recommend you do, because maths is great. If you can brute force it, even if that means leaving your computer chugging overnight, but that will find the right answer if you haven't got bugs in your code and you've tested it properly, do that. But if you're faced with something that's just, you don't even know where to start, maybe just trying a few examples, and then we can formalise it into things that fall under the umbrella of evolutionary computing, which high-level thing. You start with some random stuff and you want it to evolve into something better, for some definition of better that you need to decide. So, okay, let's start digging into this idea of better. So, Darwinian evolution or natural evolution. The theory is that, okay, if you've got some living creatures or organisms, parents will breed children with similar characteristics. And sure, we know the idea that occasionally some mutations get thrown up and the fitter ones survive for some definition of fitter. Or at least the mutations that don't make it worse continue. And then you end up with new species. And that's similar to what I said just now about start with something random. And if we can find some way of keeping some of our random scribbles on a bit of paper, take some of the better ones for some definition of better, and then give us some new things to try out, maybe mutate things a bit, then that will allow us to try quite a bit of this search space, the possible routes around all the tables and hotels. There's not time to do all of them, but this taking some of the better ones and a slight mutation from time to time means we're more likely to find something good enough, possibly the best. So, okay, natural evolution, computational evolution. Oh, I talked about scribbling on a bit of paper, but if we want to code something up, we need some kind of data structure for this. So we're going to represent each of our first initial random attempts somehow. Often that might just be an array. If you're trying to work out which order to visit the tables in, I could number each of the tables and go 0, 1, 2, 3, 4, 5. Yes, I can count. That's good. Well, 6. That's table. Can't count. So you just have an array of numbers. There might just be noughts and ones. You might say on or off for certain things, or include that, don't include that. Loads of ways to interpret Booleans. Go crazy and have strings instead, but with some form of encoding what you're trying to do into some sensible data structure for your computer. You do more complicated things like trees. We'll come to that if we get round to FizzBuzz and I stop talking so much. And basically, we initialise things. So as like I said, try a few attempts at random. If I've got an array of noughts and ones, and just randomly shove a nought or a one into several arrays. How many? Well, we'll come to that in a moment. No one knows really. Try it, see what happens. And then we see if they're any good or not. We need to give them some kind of score. Whether it's cost or a fitness, depends whether we're big or small, depends what we're doing. And now we come to the essence of all AI and machine learning algorithms. In fact, most algorithms, we have a while loop, or equivalently a for loop, and we just do something for a while. In evolutionary computing, what we do is we take some parents, we choose some of the better ones somehow. We'll talk through that in a moment. And we combine them together somehow. We'll talk through that in a moment. But if you've got an array, you could take part of one, part of the other, and then you've got a new array. Then maybe we mutate things a bit, just like we were talking about Darwinian evolution. So if we've got noughts and ones, flip a bit, or several bits. Or maybe don't flip a bit this time, but just some amount of the time, sometimes do something slightly random, just so you keep exploring so you don't miss things. Then you've got a new set of arrays to try out, or trees, or whatever your data structure is, and see how good they are, and rinse and repeat, and you might just solve your problem. Or leave yourself with some interesting questions. In theory, that should start to get better than your initial random guesses, because you're pulling out some of the better ones. And you can always remember the best ones so far. So you've always got the best one so far. And you stick with that, we might find a better one. So okay, let's again reflect what's happening in biology here and use the right lingo. So we've said maybe I could put something in an array. That's technically known as a genotype, and I'm sure if people know far more biology than I do, they'd stop telling me I'm forgetting things wrong. But it's using the terms from biology there. That's just the shape of your solution, an array with noughts and ones in, or strings, or numbers. And then we've got several of these random guesses. That forms a population with n in for some value of n. Take some parents, they make an offspring, and then that gives us a new generation. Whether the parents only live for one generation or some of them hang around for more is up to you. And, well, we've got our while loop. You probably want it to stop at some point, so you want some kind of terminating condition. So you could do a for loop instead and just try 100 times, see what happens. Or you could go, okay, that solution's good enough, I'm happy with that, and stop. Or you could, I don't know, press Control-C and just see where you've got to. Or you could let it show you how well it's doing, so you can decide when to press Control-C. So we've got our individuals, and we want to select some better parents. So we need a way of being able to put things in order and go, that one's better than that one. So we've got to give this some thought and find a way to code it up. Don't forget, I said we might want to maximise or minimise. We want a big number or a small number. Less than or greater than. That's all it's going to be when we code it up. So we'll tend to pick the better individuals, not necessarily the best one each time, because then that would have to breed with itself and that would just give us the same thing. We want to see if there's something slightly better. So we tend to pick the better ones, not always the best every time. So what you can do is you could pick 2 of your solutions, or 3, or 4, or some of your solutions, and compare their scores and take the better one from those. That's called a tournament. There are other ways of doing this, but that's the simplest thing to implement. So just take the better ones, and then 2 things. We've talked about doing the crossover. So again, that's pulling from biology, the idea of the chromosomes, and taking one from mum, one from dad. In evolutionary computing, and indeed in biology, there aren't necessarily 2 parents involved. I understand that cloning involves 3 parents, which, yeah, but that's I don't know much about biology, so I should probably stop at that point. So on the left-hand side, I've got an array with some ones, and then an array with some noughts. If we were to combine these to make offspring, then we can slice the array but from mum, slice the array from dad, and swap things over. And that gives us the 3 ones and 2 noughts for one offspring, and 3 noughts and 2 ones for the other offspring. And it might be the 3 ones is actually nudging us towards something quite good. Or 5 ones might have made it slightly wrong, so it might have made it better. It might have made it worse. It has given us something else to try without having to try everything, because there's not enough time, because we need to get to FizzBuzz. So recombination or crossover, and then the other thing we do is flip some bits, like a cosmic ray or radiation has changed your DNA and you're turning into a mutant X-Man or something, and then more things are possible. Well, if we've got noughts and ones, flip a bit. If we've got strings, then we need to use your imagination. Just do something random, but guided by a fitness function. For a while, it's bound to get better. As we mentioned, things that are hard problems, and you will see evolutionary computing techniques. Something random to begin with, representation, crossover, mutation, for a while, for timetabling. I mentioned the wedding seat planning as well, a similar way of coding up the problem. Process scheduling, lots of logistics things. So I suppose like travelling salesperson, but on steroids, loads more things to think about there. Yeah, and so on. The list is immense. And in fact, it isn't just about routing problems. You can design things. I think Andy might know a little bit about some of the background to some of these other applications. So someone managed to use a genetic algorithm to design an antenna. It doesn't necessarily look like anything a human might have come out with, but it does solve the exact test criteria they provided, and I suspect they found it useful, and that's why they made it. And you can design circuit boards as well. And again, the machine, the AI, might do something really strange, like there might be some bits in the circuit board that don't appear to be connected up. If you take them out, it stops working because the AI discovered the inductance and did something that you wouldn't do if you were a trained electrical engineer, but it works and takes up less space and doesn't need quite as many wires. So now we're going to the framework. So Chris is in charge.
Thank you very much indeed, Fran. Okay, you all right with that then? You all understand how to evolve things?
Do something random and hope for the best.
Okay, so I'm assuming you all know how to evolve things now. That's a good thing. That's a good thing because we're going to do it in code. All right, so we could throw this at you and say, let's start coding. But the difficulty with that is that you'd be reinventing the wheel because somebody's probably been here before and just might have a nice framework for us to get going with. That's what we're going to look at next. And what we'd want is a few things. Firstly, we'd want to take the framework and take our particular problem and being able to plug the problem in. And the other thing that we want to do is to set up how we do the runs. Fran talked a moment ago about how random you want it, how you do the crossover, how you do the mutation, the number of individuals. So wouldn't it be nice if you could just set up a file with all this thing in it and throw it at the framework? Sounds a good idea, doesn't it? Yeah, so why not? Well, turns out you can pick any of these ones up here. There's one, we looked at this a year or two ago back, and it was published in Overload. I've got to do a quick plug for Overload, which is the ACCU magazine. I'm sure everybody in the room's heard of Overload. If you haven't, it's wonderful. I definitely...
There were some free copies by reception as well. So.
I definitely recommend it. But the point about it is that they're in just about every language you could want to use. There's one out there. So I think the point I'm trying to make is that no sane person would start to code these up from scratch.
Apart from me in my book, but that's because I like tinkering and making things out of stuff and deconstructing things. But that's a hobby thing, not a serious...
Exactly.
Need to get FizzBuzz done by 5 or so. Yeah. So we haven't got time for that this afternoon. So
let's build on what's gone before. And the one that we've picked for today's practical is the JCLEC, the Java one, simply because I've done some work with the people in that field. So I can always ask them, why doesn't this work and what's happening there? So we picked that one. So that's it, really. The next thing we want you to do, it's up to you. You can sit back and enjoy and just chat, or you can pair program, or you can have a go yourself. It's entirely up to you. If you do want to program, have a go at this lovely framework. It's on sourceforge.net. Have a look at it. Depends on what kind of IDE or editor you want to use. In the lovely workshop we did on Tuesday, we're very flexible on this. Whatever works.
Though the audience found, I think, that in third place was, hang this, I'm going to use a Python framework instead. In second place was, I hate IDEs, I've got it working from the command line. And in first place was, what on earth did Eclipse just do? NetBeans was much simpler. So That was just
True.
based on a very small sample size of about 12 on Tuesday, so it doesn't necessarily extend generally, but it's a data point.
So, thanks, Fran. So, what worked for me is that there's a base file to start with, this jclec4 base, which has got the bulk of the stuff. So we'll need that one first, and then there's another one in there that's got a couple of kind of example problems that we need to get with second. There's another file in there, but we don't need that, so I'm just going to gloss over that one. You can copy Eclipse or NetBeans if you want. You don't have to. What I did was just get the source. Because it complies with a Maven type build, you've got to get it from the net.sf.jclec package structure. We'll come around and have a walk. We'll walk around, and if anybody wants any help, we'll be very happy to do this. We'll spend about 5 or 10 minutes on it, just getting going. But don't worry if it doesn't work, because I think these two gentlemen at the front have done this before, so they're experts. So we can always pair you up with these guys if you want to see the code. So that's the one out of the base. If you do it that way and you don't do the Maven build, you'll need the 5 library files that it needs. So you'll have to have the lib files as well. Tell your IDE about that. And the examples, I suggest you make your own package for those. It'll look something like this, but they should be on the same level as the net.sf.jclec. I've given you a hell of a lot of detail, so I'm going to stop now. And
jclec, the base files that's got the SourceForge library in and the tutorials, put them somewhere, and you might be able to build it from a command line. I think we're going to look at the OneMax problem.
Yeah. Should we take a moment just to see how people are getting
Stop
along?
talking. Well, we need to call things back together, I think, because time's running short. Can I suggest that time's of the essence and we could all mob program with Paul at 5:30 and work out what his NetBeans installation did? And so on the slides that you download, there's another example of coding your way out of a paper bag by firing cannonballs. But we'll work through that in the bar later on or something, because we need to get to FizzBuzz. That's why we're here. I can't remember what the slides were after all that excitement. I've seen right inside the framework, and I don't know what we've done to Paul's NetBeans. I'm sorry. I pressed a button. It looked like it was getting better, but it wasn't. So anyway, we can turn all the bits on in an array, and then if you've got time to play around with my paper bag escapology goings on, that moves on to not just noughts and ones, but other numbers as well. And I've written a book, and it's a chapter in the book as well, so you'll have a chance to play with that another time. Let's talk about FizzBuzz. We know what FizzBuzz is. We know it's really a drinking game, but it keeps being used to interview programmers to see if they can actually write code. Instead of going 1, 2, 3, 4, 5 and counting up to 100, you replace every third number with a fizz. So 1, 2, fizz. 4, and then buzz for 5, and of course this means for 15 we want FizzBuzz. Can we get the computer to do that? Can we do it ourselves? Well, we've looked at a sequence of trying to evolve a sequence of just ones just now with mixed success, but the problem was me helping with NetBeans rather than the framework not working. And here we want the sequence of numbers. So perhaps the computer can come out with FizzBuzz. We need more than just noughts and ones now, though. So again, we can use the framework for this. We can set up some constants. So instead of having strings everywhere, we could have some constants to remind ourselves what we're actually going to print out when we get there. So maybe set up constants. Other ways of doing this? In the way. And I know it's gone straight to enjoy the programming.
I think we can go through a few slides here. Yes.
So just go forward.
Yes, please.
Yeah. Okay. So you can use a variant on the OneMax class we've just done. Still want 100 things, but you're going to need to do something else in the fitness function. So one way of setting it up. Well, we need the fitness function. So what we could do is we could generate a sequence of what we need from 1 up to 100 to check we've got the right thing, and that will work. There might be those who suggest that we've then coded FizzBuzz ourselves in our fitness function in order to check that the computer's generated the code for FizzBuzz, and they might say that's not very successful. But it's a step in the right direction. I think it'll work, and if it means the computers then learn how to do FizzBuzz, the computers still learned how to do FizzBuzz, but we had to do it as well, so not completely automated. And for the config files, going to be similar to last time with some pertinent differences that are highlighted that I'm going to have to concentrate on what they are. So we're doing the elitism selection. Again, same class there. I think that means it's keeping the better parents, and if the kids are good enough, then they kill off some of the other ones that weren't good enough.
Perfect.
The elitism is just keeping the better ones. Like I said, you could just sweep all of the last generation away and make a whole new one, but this one lets some of the parents live for more than one generation. The elitism bit. What else are we doing? Random numbers, and if we all use the same seed in the same pseudo-random sequence, we should see the same results. Gone for 3,000 generations. Wow, that's more than we needed last time. FizzBuzz is harder than OneMax. So,
well, in OneMax we just had a 0 and a 1, so the range of values was 0 and 1. Here the range of values is 0 to 100. So you've got a stream of 100 integers, and each one of those can be 1 to 100. Or it can be FizzBuzz or FizzBuzz. So that's why it takes longer to evolve, because each one is much more complex.
Yeah. So
thanks, Fran.
The length's 100 still, and then we need some slight variations, like what you've just said, more noughts and ones going on. So we need to tell the framework a few more numbers than just noughts and 1. And is there some more on the next one?
Yeah, I think
so FizzBuzz class, tournament selector again, with 2 each time, and then thing dropping out to see what's happening on the way, to see if it's getting better or not. And, well, our fitness function, we've set up in the initialization of the class the values from FizzBuzz, where we had to code it ourselves to help the computer. That's all right. And we just give it a score from, I guess, 0 to 100.
Yes.
Demonstration.
Okay.
I didn't do a demonstration.
All of the files for that, they're on the website. So you can just go and get them and you can run them. But we do have a problem with it, which is what Fran's going to explain just now.
Yeah, so we saw when we set this up, we coded FizzBuzz so the computer knew what numbers it was after all the time. And as I mentioned in the lightning talk the other day, the best thing to do when you're stuck on difficult IT problems is harass Kevlin Henney, or remember that he's already talked about it in a talk. And go, Kevlin, you know those 8 properties that hold true for FizzBuzz? Can you remind me what they were? And he did, so that was nice. So, and actually, I quite like this. If anyone's come across property-based testing, if you can state properties that need to hold, then you can test those, and then that avoids you sometimes in your test you do a magic number and you try for one or two specific things to see what happens. If you can reset your problem in terms of the properties that need to hold true, so every result should be a fizz, a buzz, a FizzBuzz, or a number. Now, it might be in our config we set it up so those were the only things that could possibly happen. But you should just check that anyway, that's the thing. And then all the numeric results correspond to the ordinal position, and so on. We want the third result to be a fizz, and so on. So now we've got 8 properties. So now we can give things a score between 0 and 8. We don't need to code up FizzBuzz ourselves, which is like progress.
Mm-hmm.
So set them up as code. This looks slightly like Python. We'll come back to that in a moment. Now, we've done arrays so far, and with the jclec, said it right, yes, set up, that will give us an array of the numbers and go, bosh, FizzBuzz for you. And we know about the crossover and the mutate. What if instead of using an array, we used a tree structure? What can you represent with tree structures? Abstract syntax trees? Anyone? So if we can do tree structures, then we've got code, which means we can make the machine come out with some code for us without us having to code up FizzBuzz. If we actually cheat, and I'd like to explore more, and you're not going to like what I've done and how I've done it, but it works. So we've done arrays, and it's 5:10. Trees, same idea. You just choose a node in the tree as a split point, one from one side, one from the other, new tree. Things can go wrong. You might end up with syntactically invalid code, and then, well, you can either just kill that off or go with a fitness score of 0. So it might be in your fitness function, you only get round to testing the 8 things if something doesn't blow up first. So you might need to try accept around the evaluation, implementation detail. But moved on from arrays to trees, which means we can generate code. Now, that's not in the Java framework, which is why I went off-piste and played around with something else in Python. This is quite powerful. There's some things it can't do that jclec can do, and there's some things it can do that jclec can't. Any framework's got better at some things and worse at others. And I'm just starting to learn this. I think we can learn it together. Or you can go away and play with it and write something up for overload, and then I'll learn loads from it. But this does allow the tree structures. How do we evolve trees? Well, there's an example, and it's in the symbolic regression section that it works through. And that's trying to find a polynomial function that takes on specific values at specific points. But we're going to come out with something else. You set up a primitive set. So you tell it what instructions you want to use. This library, the deep library, doesn't actually use Python's internal AST representation. They've written their own to make it quicker to compile and check. So you have to manually register all the functions you want to use. In theory, you ought to be able to use the AST of the language, but that's something that we haven't got time for and I've not researched properly. They aren't doing that, which means I need to manually say things like, I want to use the max operator, and that takes 2 inputs. Or I can add some terminal values, so that a leaf of a tree of 3 or 5 or 15, it's not like I'm spoon feeding it, or maybe it is. And then you can make it generate the tree and see what numbers you get out. So I, in desperation and running out of time, gave it a if then else idea, I told it about mod 3, so it didn't have to find the 3. I told it mod 5, I told it mod 15, and I chucked in a both or an either, so like an and an or. I can just give it the mod operator, and I can say you find the numbers yourself, only then it was tending to either fizz or buzz, and I hadn't tuned the parameters well enough to quite work out that, so that this was desperation. Go, look, you must be able to solve it with these primitives, that will work. And then you set up all the things you need, and also we want some strings to output. So I told it about buzz, and I told it about fizz, and I told it about FizzBuzz. So set up. As I mentioned, you can say, oh, choose a random number for this tree. And then I realised a little while later, hang on, it needs to find 3 and 5 and 15. So I should have given it at least 3 of those as well. So yeah, it's quicker not to do that, but it feels deeply unsatisfying. And then we tell it our fitness, and we know our 8 tests. So it's going to get a score between 0 and 8. Set up a toolbox, register things we're doing. This generation is a half and half thing. So I think half the time it crosses over trees, and the other half time it grows new parts. So there's more things you can do once you've got trees than just decide where to put split points. That's another thing I could play with, and I've not experimented and kept proper notes on this. And also you control the size of the trees, and some of the trees will get really big really quickly, and there's lots of rumours and myths about starting with about 2 and never going beyond 17 crops up loads. I can't recall why Koza said that, or if it just happened to seem to work. We haven't said who Koza is yet, but there's not much time, we might get there. Set things up, and then leave it to it. Yeah, as I said, there are other options than just this half and half thing. Sometimes grows, sometimes swaps bits around. And then a fitness function we just nicked from Kevlin. It's got the 8 tests, which are all the ifs, and just a safe run at the top in case the tree structure it's come out with does something really revolting, like divide by 0 or something horrible. And then when we've got all our ducks in a line, our tests, which didn't involve us writing FizzBuzz ourselves, which is good, but then we spoon-fed it the mod 3 and the mod 5, but he could guess some numbers if it had a bit more time. We tell it what we want to keep track of, and one important thing here is I said, as you're exploring, if you remember the best one so far, and the parameter in this is called the Hall of Fame, where this has stored the best one so far, and if anything gets better, it'll store that. We can ask for loads of statistics, so like the listener in JClex, see how it's going, see if it is getting better, see if it's got stuck somewhere and stopped getting better. These are important things that we've not looked into much. And then send it off, let it do its thing, and then we see what the final population is, the log of stuff that's happened in the Hall of Fame. And eventually, with these parameters, it did generate FizzBuzz. I already showed the code in the lightning talk. Because it's not using the AST, I'll then need to write a tree walking algorithm to pull out the stuff I did to actually generate a Python file. But as a string representation, now when Steve said this is the best one, this is number 1 in the Hall of Fame, when hubby Steve looked at it, it's like, what has it done? Either FizzBuzz or FizzBuzz, 4th line down. If you glanced at that in a code review, you say, hang on, what are you doing there? But it needs to come out with things that are valid and will compile and stuff, and this is what happens. So there we go, Hall of Fame. It did come out of FizzBuzz. Try and download the deep framework and play with it, or if you're like me, you might want to actually try and do something like this yourself with the abstract syntax tree. Or if you're like Chris, you'll want to find a framework that actually just works and play with that. But if someone can do FizzBuzz less horrifically than I did and end up with the HOF that we did that joke in the lightning talks, then please write it up. But that is really interesting. You can actually get a code to generate some code doing exactly what we did with the OneMax, really. Try something random, crossover, mutate around a bit, but you need really good tests. So you might need some help from Kevlin if you go down that path. You're going to round things up?
Yes, thank you very much.
I'll give you 10 minutes.
Okay. Thanks very much, Fran. So, we've got code to generate code. Have a little think on that for a moment. We've cut the human out the loop.
Apart from Kevlin writing the text.
Well, yeah. So, has anybody else done this before? And lo and behold, if we go out into other fields, yeah, lots of people have evolved these tree structures. So they've got this gene-based programming way of doing things where they've got this mathematical function, as Fran was saying before. And what we want to do is to define the operators, terminal nodes and things like this in a tree structure and just get that to evolve. And lo and behold, this has been around for quite some time, particularly in the hardware field. So circuit boards have been built by this way. And apparently the people that have built the circuit boards claim that they can get better approaches to the circuit boards using these techniques than a human being can, which strikes me as quite interesting. But what does that mean for us when we're actually building software? Could we use GP, this gene-based programming way, to evolve code for FizzBuzz? Well, the answer is yes, we can, because we've just seen it happen. We've seen it with our own eyes. We know that we can do it. But, and this is the big but, it doesn't look like what a human being would produce. Now, that's quite a big factor. And also we find, if a human being had to code FizzBuzz, how many lines of code would that be? A mod 3, mod 5, and a mod 15, and you're just about there, aren't you? If it took 15 or 20 lines, you'd be there.
So Kevlin can do it using sed in about 4 lines, but that's...
Fantastic.
That's some benchmark.
Fantastic. But as we saw here, well, was it one line of code, but it filled an entire slide?
Well, I don't know. I think with all the ifs and elses, it would go that way. And there's more to code than the lines of code. There's also it didn't even seem worth trying. If the machine can run it by itself, then I'm staying out of it.
So what's been really good, some of the talks I've enjoyed at this year's ACCU were about the meaning of code and how people understand it and how important it is to be elegant and just right. And I don't think GP is at the state where it could build anything of a realistic scale. There's reasons for that I won't go into, but there's a thing called code bloat where the trees just get enormous. And then it depends on the human being to start to trim the trees, and then kind of not where we would have been.
Mind you, on the other hand, if your customers can write the tests accurately of exactly what they want to happen, and the code gets generated, you'll never ever have to fix a bug. You won't ever have to look at the code. Be fine, as long as the customers can be really, really precise up front about exactly what they want.
True.
It'd be fine.
What could possibly go wrong? So the question is, maybe it would be better to start with code that we've got and pick bits of it that we wish to improve. And lo and behold, this is a rich research area that's going on at the moment where people are using GP to improve code, to refactor it, to get it to perform better. Again, it depends on your tests. Yeah. Just as Fran said, take a chunk of code that you know needs to be improved, define the tests, build up an abstract syntax tree, because you're going to do that every time you compile the code anyway. So, you've got the tree there. It all depends on the tests and the tests that you want to run. And then you might come back to me and say, well, that's a whole bunch of code, Chris. Isn't there a framework that I could get going with that? Well, actually there is, and it's called Gin, which I think is a nice...
And it's nearly time for the bar, so that's great.
So I personally think this is where it's going to go. So I don't think we're quite out of a job yet, as per Fran's lightning talk, because it's producing functionally okay code, but it's not what human beings would understand that to be. And that's a bigger issue to discuss over a beer.
As a side point, I don't think we've got a slide on. I touched on the idea of property-based testing earlier. And that will come out with random values to slot into your code to see whether it fits the properties you described.
Yes.
And I know a guy and some others who are working on Hypothesis, which is property-based testing tool for Python. And he's pulling on some of the genetic algorithm and evolutionary programming research to do what they call shrinkers, to try and zone in on ways to job over your properties that you want. So there's a nice, so there's not just the code, also the testing. And then there's Austin Bingham's Cosmic Ray Python framework that mutates your code to see if the tests still pass, which tells you your tests were rubbish. It's all really about testing and making the code nicer. So much.
And one last thing from me is that, well, if we're saying that it's important that human beings have to read this and work with it, well, why don't you put the human being in the loop? Why don't you say that the human being can offer a fitness measure? Why don't we take elegance? Why don't we take understandability in some way and ask a human to guide the search as well?
Like the smiley faces at the back of the room, that'd do.
Absolutely.
Which reminds me, there's smiley faces at the back of the room.
Another area that's really interesting in this field is where the AI takes this piece of code, or takes a model, or takes a test spec, and quantitatively evolves it. But from time to time pops it up in front of a human being and says, do you know, am I on the right track? Tell me what you think about that. And that's where I think AI is going, particularly for how we program. We can't get by without the human being. The AI isn't at that point yet. But if you put the human being and the AI as a team and put the human being in the loop, then yes, we will get somewhere. And that takes me on to the last slide. Thank you very much for your patience. On the left-hand side of the slide is one of the best books I've come across in many a year. Honestly, it's a really good book. Fran's book takes the idea of evolving out of a paper bag, and that's a great metaphor. So she starts with machine learning techniques and particle swarm optimization and ant colony and hill climbers and iterated local search.
10 chapters.
Yeah, all these manner of ways to get out of a
Got a few copies left and some paper bags to put them in if you're interested.
Okay, so
Fran, if you need a tax receipt, I wrote one on the paper bag for Anna Jane earlier.
Fran now owes me a gin and tonic for the plug.
I shall. Chris has written a really interesting paper, so we can...
And some of the research I'm doing at the moment is exactly that, putting the human being and AI in the same place at the same point in time. So there's mutual learning. The AI learns about the person, and the person learns about the AI. So you've got this mutual learning going on, which means that you're achieving things that you couldn't achieve with the AI on its own, you couldn't achieve with the human being on its own. You have to put the two together. And if you want a reference to that, in fact, the people that I did it with, some of this work are in Spain, and they're the people that did the JCLEC framework, which is why I'm quite friendly with them and I know how it works. So, thank you very much indeed for your attention. Hope you enjoyed it. Please feel free to click on the thing at the back, and please give us any feedback. We're going to the bar. We would love to chat to you further over the bar.
So half an hour to round up a drink, and then some lightning talks at 6 o'clock, I presume. So half an hour natter if you want. If someone wants to ask a question, that's fine. But I think the time's up, so just come and natter instead.
And lastly, because you worked so hard and you did all the coding, why don't you give yourselves a round of applause? Thank you.